Okay, we need to also implement a process cell. So this method will perform the propagation on the propagation pair. So we will need to call if output grid, check if cell is collapsed, and call propagation pair cell to propagate position. So if the cell is collapsed, we want to enqueue its neighbors for the propagation. We want to do it because if we have collapsed a cell, we need to check if the neighbors can still have solutions. So propagation helper, enqueue uncollapsed neighbors, and we need to pass it the propagation pair, and we need to create this method. So let's go and generate the placeholder. Let's go to the definition. Okay, and here we will create var uncollapsed neighbors, and we'll make it equal to core helper dot check if neighbors are collapsed. We pass it propagation pair and output grid. So you might recall that this returns a list of neighbors that are uncollapsed yet. For each, now we want to loop through those uncollapsed neighbors and call pairs to propagate, enqueue, and item. And we can change the name from item to uncollapsed. So we get the propagation pair with a uncollapsed with a cell that is collapsed, so we can check the neighbors if this collapsed cell didn't block them from having a solution. So we enqueue them simply to the propagation queue, and then we can propagate through them and check them. Okay, let's go back to core solver. We have else. So if cell is not collapsed, we call propagate neighbor. So it is a new method that takes propagation pair. So propagate pair, and let's create this method. So this method will have the logic to actually propagate the cell. We need to create var possible values at neighbor equals output grid, get possible values for position, and propagate pair, and cell to propagate position. So we get the possible values for the cell to propagate. Next we create the int start count. So what is the number of possible values currently? So possible values at neighbor dot count. And next we want to remove impossible neighbors. So this is a new method that takes propagation pair, propagate pair, and our list of possible values at neighbor. And this will remove the impossible neighbors from our possible values at neighbors list. So we will be able to check if at the end we have solutions, or we have a collapsed cell, or we have a low entropy cell. And let's finish this. So propagate neighbor, and we need to create an integer value of new possible pattern count. So this is after propagation. We call possible values at neighbors, because we will be modifying this list, and count. No basis, okay. And actually this is not a list, this is hash set. So possible values at neighbor is a hash set of integers. Great. And we need to call propagation helper, analyze propagation results. So this is the third step. We analyze how the grid looks after the propagation. Actually, this is how the cell looks after propagation. Propagate pair. We pass it propagate pair, start count, and new possible pattern count. We have implemented this method previously. Okay, so this step actually just analyzes if we have anything else to do or if the output grid is compromised and we need to restart the whole process again. Okay, let's implement the remove impossible neighbors. So this is the core propagation logic. We need to create a new hash set of integers. We call it possible indices equals new hash set. And now we will loop through each pattern index in output grid get possible values for position and for base cell. So for each var pattern index at base, in output grid get possible values for position, and we pass it propagation pair base cell. So you might remember that propagation pair is made of cell to propagate and a base cell. Our base cell is the cell that from which we are propagating. Its indices will want to influence the cell to propagate indices and reduce them. And that's why we are looping through the possible indices in our base cell, and we will be adding them to a hash set. So creating all possible indices for our neighbor. So we need now to create var possible neighbors for base equals pattern manager get possible neighbors for pattern in direction and pattern index at base and propagate pair direction from base. Okay, so now we have all the neighbors for a given index, for that could be a solution for our base cell. And now we add to the possible indices for the neighbor to possible indices hash set. Possible indices union with and our possible neighbors for base. So as I said previously, we are creating a hash set of all possible indices that can be in our neighbor. And now we will call possible values at neighbor intersect with, pass the possible indices, end up with a intersection between two sets. And if it is 0, it means we have a collision. If it is 1, it means that we have a solution. And if it is more, then we have a low entropy. Okay, I see we have an error here, and we are missing brace. Great. Now we will implement a method called getLowestEntropyCell, which will return a vector to int. And this method will return a low entropy cell for collapsing in a collapse cell step. So if our propagation helper lowest entropy set count is less or equal to 0, we will return a random cell. Output grid get random cell. Else we will get the lowest entropy element from our lowest entropy set. So var lowest entropy element equals propagation helper lowest entropy set, and we will take first using a link library. You import using system.link. Okay, and now we need to access the position. So now we will create a vector to int return vector and assign it to lowest entropy element position. Next, we need to remove it from our set. So propagation helper dot low entropy set remove and lowest entropy element. And next we return the return vector. So that's why we either return a random cell at the beginning of the algorithm, or we search for the lowest entropy cell. Next, we will need to create a collapse cell method that will do the collapse cell step logic. So let's create a method will be called collapse cell, and it will take a vector to int cell coordinates. Next, we will create a var possible value equal to output grid get possible values for position and pass it the cell coordinates and create a list out of it. So output get possible values for position cell coordinates, and we will call to list link method. And now we will call if the possible value list is equal to 0 or 1, we will return, because we know the cell is either a collapse or either it is a collision. So if possible value count equals 0 or possible value count equals 1, return. Else we will create int index equals core helper, and we will select solution pattern from frequency and pass it possible value list, possible value. So basically this step creates an integer that index that is the solution for our cell. So this is the collapse cell step. We create an index that will be a solution, and we set this solution by calling output grid set pattern on position. And we need to pass x and y, so we need to pass cell coordinates x, cell coordinates y, and the solution, so index. Because we have collapsed a cell, we want to check the neighbors if we haven't created the collisions, and we will call an if check and core helper is check cell a solution for collision and pass it cell coordinates and cell coordinates and output grid. Okay. And if this is equals false, we call propagation helper and add new pair to propagation queue. Okay, apparently we have set the add neighbors, new neighbors to private, so let's go to the propagation helper, and add new pairs to propagate queue is actually private, so let's change it to public. Save it, go back to core solver. Now we should be able to call add new pairs to propagate queue and pass it cell coordinates, and as base cell coordinates, since this is the first step, this is the collapse step, so we don't have the base tile for it. So if this returns true, we need to set propagation helper set collision flag. So we have experienced a collision. Okay, great. Next we need two additional methods, check if solved and check for conflicts. So public bool check if solved will return output grid check if grid is solved. Okay, we can change the name to small o, the letter, and we are just returning the same values that we have in the output grid, because we have the same method in the output grid, but we don't want to have placed it inside the method, so let's go one brace below. Okay, now we are in the class context. So basically we are returning the same what we could have asked the output grid, but we don't want to grant access to other classes to access the output grid. Instead we want to create methods that will output these values that we call on output grid. So last method we will need to check for conflicts, that returns also a bool. And we will return output propagation helper check for conflicts. Okay, this was the last method here. So we now should have a complete core solver, propagation helper, low entropy cell, core helper, vector pair, and output grid. And next video we will test if our propagation step works. Okay, so now to test our wave function collapse core algorithm, we will need another helper class that will contain all the logic. So we will only call it and it will perform the algorithm itself. So let's create another class called WFC core. Let's place it in our namespace and delete mono behavior inheritance. Okay, here we will need to create a couple of fields, output grid and pattern manager. Okay, next also a private int max iterations and initialize it to 0. Okay, Now let's create a constructor. In the constructor, we will take some parameters that the user gives us and some other classes that we have previously created. So we will pass int output width and int output height. And also pattern manager and int max iterations. We can move the int max iterations before the pattern manager, since those three int values are passed in by the user and pattern manager is created beforehand. Okay, let's assign this output grid to a new grid that takes width, height and pattern manager, get number of patterns. So equals new, and we'll pass width, output height, and pattern manager get number of patterns. We will also assign pattern manager and max iteration variables. Okay, great. Next we will need to create a method called create output grid. I need to fix the names. Okay, so let's get back to creating the method called create output grid. It will return a jagged array of integers. And we will call int iteration equals 0. So this will be the count of iterations that we have already passed, and we will measure by this variable how many times we need to iterate before we stop. Okay, so while loop and iteration less than this dot max iterations. We'll create core solver, call it solver, and instantiate it as a new core solver, pass it this output grid and this pattern manager, and call int, create int inner iteration equals 100. So there might be a case when our propagation fails and propagation goes infinitely. So one propagation, not the whole algorithm, but the propagation step. So the cell is added and removed and added and removed, and that's why we create this inner iteration equals to 100 to prevent the inner iteration to be to go more than 100 times. And if you create a bigger picture or bigger output image, this might get in your way, so be sure to check or change this value for a bigger pictures, or maybe pass it in from the user. Okay, let's delete an additional letter and create another while loop, and we call it if not solver dot check for conflicts, and if not solver check if solved. So if grid isn't solved and if there is no conflict, let's create vector to position, vector to int position, and it will equal to solver get lowest entropy cell. So we get our position, call first step, so collapse cell on the found position. So this is the core algorithm code. Next, solver dot propagate. Next, we decrease inner iterations and check if inner iterations are less or equal to 0. We will print debug.log propagation is taking too long, and we return new int jagged array of 0, 0 and empty square brackets. Okay, after this while we must analyze the third step, analyze. So solver check for conflicts. So we will know if there is a conflict or not. If it returns true, we debug log that conflicts has occurred and restart the iteration. So that's debug.log /n to write in a new line and conflict. So conflict occurred, iteration and the iteration number. we add to iteration, and we call output grid.reset. Okay, I think we have this method private, so let's go to our output grid. Let's find the reset, and we change it to public. Okay, let's go back to WFC core and call reset our possibilities. Great, and solver equals new for solver. So we create a new solver. This.output grid, this.pattern manager. Okay, and if there was no conflicts, we call debug.log solved on iteration. And we will create an additional method in the output grid called print results to console. So this.output grid print results to console. And we break out of this loop. Okay, let's make sure that the name is okay, and let's create the placeholder for this method. And let's finish this by creating another if statement. If iteration is greater or equal than this dot max iteration, we'll debug.log and couldn't solve the tilemap, and we return output grid get solved output grid. Okay, so if we do everything okay and the core solver solved the output grid, this loop will stop, and if we didn't go past the max iteration, we'll return the solved grid as an jagged array of integers which contains the pattern indices. So we will need to map it yet again to back to the tilemap. Okay, let's create our additional method in the output grid. So we can go to the test class that we had before and copy the path with the string builder if you have not yet deleted it. And let's go back to our output grid, and we can paste it here and uncomment it. And if not, you need to rewrite this. We will need to use system.text, okay, and we will change in the loop. So for rows, we will call this dot height as the limit. For row from calls, we will call this dot width as a limit. And here inside the loop, we will call var result equals get possible value for position new vector to int and pass the column and row. And if a result count equals 1, so we have only one value, so this cell is solved, we can just append to the builder this result. So result dot first will get the first value and add an empty space. Else, so in case we didn't solve this output grid, we need to create string new string equals empty string, and we loop for each var item in result, and new string plus equals item, and we add a comma, and we append the string to the builder. We can print an additional division line with 3 dashes, and we're good to go. So now we have working with WFC core. We will create it and get the result for testing purposes. So let's get back to our test class. I will need to clean up this class a bit, so let's delete everything from here. We will need to leave the input grid, the value manager, the pattern manager, and manager process grid. And we'll call WFC core. Core equals new WFC core. And output width and output height we can pass 5, 5. Max iteration we can make it 500. And pattern manager, manager. And what we need to call is var result equals or create output from grid, and this should create our result. Okay, so let's go to Unity and try it out. Let's run our class, our Unity. And we can see that after 383 iterations, it has solved our grid using a pattern of size 2. Now let's try using a pattern of size 1. Let's go back to our test class and pass 1 to the manager. Save it and go back to Unity. Okay, clear the console and let's run Unity again. And we have a score, but strangely it is all zeros. So why is that? Well, we have some bugs in code, so let's go back to core solver. Okay, so in collapse cell, we are passing index to the output grid set pattern on position method, but actually we want to pass possible value index, as we are retrieving a solution that is an index out of the possible indices from the possible value list. And we have passed the index as value, but at the index of possible values there might be another number. So this was one of the bugs. And another bug was in pattern data class. If you open it, we have a private int frequency, but actually we want to initiate it to 1 at the start. So after creating a pattern, we already want it to be 1, and then we will be adding to it. Okay, so let's get back to Unity. Let's clear the console and let's play it again. Okay, and we have the same result. Let's try it again. Okay, and I believe it should be working properly right now, because the values are not really zeros anymore. They are changing, and if we run it a couple more times. But for clarity, let's stop it and let's change our tilemap a little bit. So I'm gonna change it to grass, 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 grass. Take the road, straight road, and place it at the bottom, and take 2 trees, the 3 tiles, and place them here. And now let's clear the console, stop editing the tilemap, and let's play. And we see we should get a much faster result in much less iterations. And okay, finally I got a result that shows that we can have 2s above 1s. So remember, we start with the outline. So outline is grass, so it's a 0th tile. Above 0 can be 1, so road, and it is showing up here. And above road can be either tile of grass, so 0, or trees, which is 2. And we have experienced it here. So let's try again for the pattern of size 2. So let's edit our test class, the pattern, and let's pass it a 2. Okay, let's close it. And let's run it again. And again, we have a solution much faster in 0th iteration. And it looks pretty good. I mean, the values are different and they are showing up, and they have some patterns to them. So we are going now to the section where we create actually an output from this, what we have from our algorithm. And then it will be much clearer to see if the results are good or not. So see you there in the next video.